All right, thanks, Sean, and thanks everyone for joining. So today we're going to talk about random interval maps with holes. And so this is joint work with Gary Froyland, Cecilia Gonzalez-Tuckman, and Sandra Vienti. Okay, and so our goal is, well, we want to look at piecewise expanding maps of the intervals, and we want to add holes, okay? So in doing this, we're going to look for conformal and invariant measures, and we're also going to look for escape rates. And then, well, for the points that don't escape, we can ask what the size of these is. So we're going to look for the Hausdorff dimension of the fractal surviving limit set. Okay, so this, all of this work primarily will generalize the results of Liverani and Malm-Deschamps from 2003 and from the joint work with Gary, Cecilia, and Sandro from 2020, where we looked at the same sorts of systems, but without holes, okay? All right, so first, we're gonna start with a very simple kind of motivating example, and I've added some pictures, so please enjoy those in my very bad drawing skills. But we want to consider first the map just Tx equals, or T of x equals 3x mod 1 on the unit interval. And we're going to consider the hole, which deletes the entire middle branch. So that is, the hole is from 1/3 to 2/3. Okay. The Birkhoff-Ergodic theorem tells us that Lebesgue, almost every point, is going to eventually fall into the hole upon iteration. Okay, so that leaves us with, say, two questions. We can ask, at what rate does the mass escape through the hole? Okay, and we can also ask, what is the size of the measure zero fractal surviving set? Okay, so in terms of the escape rate for this system, it would just be log 3 minus log 2, and the Hausdorff dimension would be log 2 over log 3. And this is a very particular example because, well, our fractal surviving set is just the Cantor set. And so we'd be looking at measures on the Cantor set. Okay, but we want to look at this more generally, and even more important, we want to look at a random dynamical system version of these sorts of problems. So first, maybe let's talk about, in general terms, what is a random dynamical system? So for a random dynamical system, we'll start off with a base probability space and some map sigma on this space omega. Okay, and for each omega, each fiber omega, we're going to, say, attach some map T omega from some, say, compact metric space X into itself. All right, so we're going to iterate these maps accordingly. We'll do T omega to the nth iterate. That's just going to be the n-fold composition of these maps along the sigma orbit. Okay. Why should we care about these? Well, random dynamical systems are going to more realistically model real-world systems than deterministic systems. And in terms of what we'll talk about today, we want to put a hole into these systems to, well, model some sort of physical process that has some sort of trap or some sort of absorption in it. Okay. Now, what we'll talk about today are piecewise expanding interval maps. And we'll start off with some more assumptions on our base probability space. We'll assume that our map sigma is going to be invertible and ergodic, and it's going to preserve the measure n. And now for each of our fiber maps T omega, these will assume are going to be piecewise monotone. So we have some finite partition Z omega 1 of monotonicity. And we'll also assume that T omega is going to be onto. It's going to map the unit interval onto itself. And for each of our monotone pieces, T omega Z is going to be an interval, and T omega restricted to Z is going to be continuous and strictly monotone. Okay. Now, our primary tool is going to be the transfer operator, and this transfer operator is going to act on the space of BV functions. So first, we should really quickly recall what it means to be a bounded variation. And it just means that this variation over the sum of all possible finite partitions is going to be finite. Okay, the space BV is obviously a Banach space with our norm variation plus sup norm. And notice here we want the variation plus sup norm instead of maybe the usual variation plus L1 with respect to Lebesgue. And the difference here in terms of randomness is we're going to look at the space BV omega 1, or rather BV omega I. And that's going to be all the functions who on the omega fiber are BV, and the BV norm is going to be measurable. All right. So now we want to define our transfer operator, and we're going to define that first for the closed system. So that is the system without holes. And so we'll let SNT be the usual Birkhoff sum, where here we're taking the Birkhoff sum along the sigma orbit. Right, and we're going to consider a general potential. We'll let phi c be some function in BV omega I. And here the subscript c and throughout, whenever you see a little subscript c, that's going to denote on the closed system. Okay, that is the system without holes. All right, so we take a general potential phi c, and we can define our general weight, g omega c in, just to be the exp of the Birkhoff sum. And then our transfer operator is defined in the usual way, is just the sum over the inverse images of this weight function times our function f. Okay. And for the usual potential, phi omega c is just minus log t omega prime. This gives us the usual Perron-Frobenius operator. Okay. Now, before we get to holes, we need some more assumptions on the general closed system. And so what we're going to assume is that there exists some random probability measure nu c, which is going to be our closed conformal measure, meaning that it satisfies this property that nu sigma in omega of c of our n-fold push forward is going to be equal to some lambda to the nth power times nu of f on the omega fiber. Okay. And this is going to hold for any f in BV. And additionally, we also want to assume that this lambda omega c multiplier is going to be log integrable. Okay. So in our previous paper, we with Gary and Cecilia and Sandro, we proved that such measures exist for lots of classes of piecewise monotone interval maps. In particular, basically, if the map is expanding on average, and our potential is what we'll call contracting, these sorts of measures will exist. Okay, and in fact, we'll get an exponential decay of correlations and lots of other nice properties, but this is all we'll require. Okay. So now that we've clarified our closed systems, let's talk about open systems. And so by an open dynamical system, I mean that we're going to poke a hole in our phase space. So we're going to let h omega, for each omega, we're going to let h omega be some subset of our unit interval that has positive closed conformal measure. Okay, so for these purposes, you can just think of h omega to be some interval or a finite union of intervals. Okay, now some extra notation. We're going to let I omega be our unit interval, take out our hole, so just the complement of our hole. And now, like we said before in our motivating example, the Birkhoff-Ergodic theorem tells us that almost every point, almost every here is with respect to our nu omega c conformal measure. Almost every point is going to eventually fall out of one of these holes. It's eventually going to escape. So we want to define these nth level survivor sets where this x omega n is the set of all points whose orbit will not land in a hole for at least n iterates. Okay. Now, if we take the intersection over all n, this gives us the set x omega infinity of points which will never land in a hole. So these are all the points which will survive forward iteration from our maps. Okay. With all of this, we can now talk about our open transfer operator. This is going to be L omega of f. Notice we have this without the little c, which means that we're talking about the open operator, right? And we define our open operator in terms of our closed operator, where we here are multiplying by our characteristic function on the complement of the whole. Effectively, what this does is we, before we push forward, we kill everything that's in the hole, and then we push forward what's left over. Okay. Now, before things get complicated, let's talk about some simple examples you can keep in mind while we're going through this. So all the results we're going to talk about today will apply for this class of random beta transformations, which have no non-full branches, which are too short. Okay, so I'll draw another very bad picture in a second so you can have something to keep in mind. But what we mean is that a beta transformation is take any beta, say, on average bigger than 3. And we're going to consider the map beta omega x mod 1. And I want to make sure that my beta omega is such that the last non-full branch is not too small, which is what this condition that beta omega is in this union k plus delta to k plus 1 for some fixed positive delta is ensuring. Okay, so in addition, all we're going to assume is that our beta omegas are strictly bigger than 3 on average, and that the ceiling of our beta omegas is log integrable. Okay. So that is enough on the closed system to get the existence of our closed conformal measure, like we were assuming. Now, on the holes, we need to assume, well, depending on what you want your hole to be, you may or may not have some additional assumptions. But if we just only focus on holes where the hole is that last branch, that is the branch that contains the point 1, then everything will apply. So the picture that you should have in mind is our maps look something like this, where here all of our branches should have the same slope, which it's hard to draw, so please forgive me on that. But our hole is always going to be this full last branch, and that branch we're assuming is not too small. Okay, and also I guess we kind of said this before, but let me say it another way. The assumption that we need no short branches is only for the closed system. So once we have our closed system working, all we have to do to have our holes is, well, we pick this hole to be the last branch, and everything will work that we're going to talk about today. Okay. So now that we have our examples in mind, we want to move forward. Our first goal, we said, was to find conformal and invariant measures. So normally what we might do to find the conformal measure is apply some sort of fixed point theorem. That's what we did in the closed setting. That, for some technical reasons, is not a very good idea. And so what we're going to do here is we're going to follow the approach of Liverani, Zasol, and Vienti from '98, which is the same approach that Liverani and Mom-Deschamps used for their open systems. And we're going to look at this functional defined in terms of this limit of push forwards of transfer operators. And this capital lambda functional is going to be our candidate for what the conformal measure should be. Okay, so this this functional lambda satisfies all of these nice properties. Though at this stage, we unfortunately don't know that lambda is linear. Okay. Once we know some additional things, we'll be able to show that lambda is in fact equivalent to some Borel probability measure, and that satisfies the usual properties that our conformal measure would. That is, it satisfies our equivariance property that we want. Okay. So now our next goal is, well, we plan to use cones in order to get the uniqueness of our invariant densities and invariant measures. And to set up our cone approach, we need to talk about a Lossody-York inequality and some variation, and we need to talk about these partitions of monotonicity. Okay, so we're going to define our cones in terms of our capital lambda functional that we just talked about, and the same with our Lossody-York inequalities. And so we want to now define these monotonicity partitions in terms of our capital lambda functional. So at the beginning, we said z omega 1 was our partition of monotonicity for our map T omega. We're going to let z omega n be the partition of monotonicity for our maps T omega n. Okay, and now we define these special subcollections. So these z omega stars, these are just going to be all the partition elements which are contained in our survivor set. Okay, we can calculate from our lambda functional that if you're not contained in one of these survivor sets, you're automatically going to have your functional value being 0. So like measure 0, which is what we'd expect because we expect our measure to be supported on our surviving set. Okay, but from there, we need to further define these collections of good and bad intervals. Okay, so these good intervals are going to be the ones that have positive lambda functional value, and our bad intervals will have 0 lambda functional value. In terms of picturing this, you can easily calculate and show that if a branch is a full branch, then it's going to have positive lambda functional value. So it's going, a full branch will be a good partition element. Okay, so bad partition elements are going to be like the ones I have circled here in this picture. These are potentially bad partition elements. Okay. Moving forward, we're going to have some sort of counting argument in terms of how quickly our bad partition elements grow. And so we're going to need to define this notion of 2 partition elements being contiguous. And so we'll say that, say this W and Z are contiguous if they are either contiguous in the usual sense in that they share a boundary point, or if they're separated by a connected component of the pullback of the whole. Okay, so in this picture, here this red splotch, we'll say this is the whole. So we would say that these 2 circled bad partition elements, we'll say that these are contiguous. Okay. Now, for our main assumptions. Okay, so first we'll have this assumption Q1. For our assumption Q1, this is what we would call in the closed setting to have a contracting potential. So from the closed setting, we would have had the limit 1 over n log sup of g omega n is less than log of rho omega. I should go back. I forgot about rho. Rho is going to be very important. Let me go back. Rho, I'm going to define to be capital lambda sigma omega of L omega of 1. Okay, rho is going to be the multiplier we saw, the lambda omega c from before. Or rather, it's not going to be lambda omega c, but it's going to be the open version of that closed lambda omega c multiplier. Okay, so a contracting potential in the closed setting would just be the 1 over n log sup g less than the integral of log rho omega. But now in the open setting, we're going to require this additional assumption that the 1 over n log sup g is less, or rather plus lim sup 1 over n log psi omega n is less than the integral log rho omega. Okay, here now we're going to let the psi omega n number is going to be the maximum number of contiguous bad partition elements. Okay. Q2, well, we need to assume that this maximum number of contiguous bad partition elements, we'll assume this is log integrable. And this, for this Q3 assumption, we need to know that, well, if we have a good partition element, that its lambda functional value doesn't get too small. So we need to know that, say, the minimum kind of measure of our smallest good partition element is still log integrable. Okay, now these assumptions are admittedly a little complicated. So at the end, if we have time, we'll go back and give other assumptions, alternate assumptions to these that are much easier to check in terms of, say, good and not good and bad, but in terms of full and non-full branches. Okay, but for now, we can at least say that the example that we gave in terms of random beta transformations, you can easily show that all of these are satisfied. Okay. Now, with these main assumptions, like I said before, our first step in getting the uniqueness of our invariant densities and invariant measures is going to be to prove a Lasota-York inequality. Okay, so we're going to define our normalized operator, L tilde, to be, and okay, so here this lambda omega inverse, this should be a rho omega inverse. But our L omega tilde is going to be rho omega inverse of L omega. And we want to find our invariant density. Invariant, or rather density here means density with respect to our functional lambda. So by that, I mean that I want lambda omega q omega to be equal to 1. And invariant with respect to this normalized operator means that L omega tilde of q omega is going to be equal to q sigma omega. Okay. So the first step in this machinery is to prove a Lasota-York inequality. Okay, so we were able to do that in this first Lasota-York inequality, but while this q omega n and this k omega n, what can we say about those? Q omega n is going to go to 0 exponentially fast, which is what we would expect from, say, the usual deterministic Lasota-York inequality. But unfortunately, we don't have any control over the rate that this is going to 0. So this exponential rate is a function of omega, which is not great. And even worse, the k omega n terms that we're multiplying in front of the lambda functional terms, those we have no control over, and those could grow with n, those could grow even super exponentially. Okay, so this is also less than ideal. To get around this, we prove a second Lasota-York inequality, where now we're not just pushing forward, but we are in fact going back in steps along the sigma orbit, and then pushing forward so that we end up exactly on the omega fiber for every n. Okay. This is going to be very useful if we want to find an invariant density on the omega fiber, and we'll talk about that in a little bit. But in the second Lassaud-York inequality, we're finally able to get now a uniform in omega exponential decay rate, and we have some sort of control over these k omega n terms. Okay, so the next step is we want to apply the Birkhoff ergodic cone technique. So we should first talk about what convex cones are. Okay, so a convex cone is going to be a subset of a vector space that satisfies these first four properties. And now a theorem of Birkhoff says that, well, if we have some positive linear operator that sends one vector space into another, and that it sends one convex cone into a convex cone in the second vector space, then if we look at the pseudometric, if we look at the Hilbert pseudometric on these cones, well, then the diameter in terms of these pseudometrics, the diameter of the image is going to be a contraction with contraction factor given by the hyperbolic tangent of the diameter of the first cone. Okay. So this is going to be super useful, but we would like to go a step further. We would like to get this exponential contraction in terms of the soup norm rather than these Hilbert pseudometrics. And we can get that using a result of Liverani, Stasal, and Vianti. Down here at the bottom, we see that, that the soup norm distance between F and H is going to be less than the exp of the theta A norm of F and H minus 1. Okay. So that's going to be how we can translate that Birkhoff result to actual distances of our functions in terms of the soup norm. And now for our random cones, we want to look at this C omega plus and the C omega A. Okay, where the C omega plus is just going to be the cone on the omega fiber of all non-negative BV functions. And then our A cone, well, this is going to be a subset of our C omega plus cone, but the subset where our variation is less than some parameter A times our lambda functional value. Okay. Now, these are the types of cones that we expect to get our exponential contraction in. Now, we want to look for this exponential contraction, but when you start working on this, it becomes very obvious that this will not work for every fiber. Okay, so what we have to do is we have to restrict to some, say, large measure set of good fibers. So we can do this for every epsilon. We can find a set of measure greater than 1 minus epsilon of fibers, which we're going to call good. And by good, we mean that if we push forward our C omega A cone by some explicit positive finite number R star, if we push forward a good fiber cone by R star, we're going to get contraction by a factor of 1/2. Okay. Now, for the small epsilon measure set of bad fibers, well, we can still get contraction by a factor of 1/2, but we're going to have to push forward by more than R star. We have to find, well, for every bad fiber, we can find some number L omega between 2 and it's finite for almost every. So some positive finite number L omega, such that if we push forward the C omega A cone now by L omega times R star, well, now we finally get the contraction by a factor of a half that we want. Okay, so now for both good and bad fibers, if we push forward by a specific amount, we'll get contraction. The problem with just looking at good and bad fibers, though, on their own, with just the R star and the L omega R star, is that for some technical reasons, we were not able to estimate the diameter, the size of the diameter. Okay. To remedy this, though, if we again look at pushing forward our C omega A cone, we can find some very large omega dependent multiple of R star, where if we push forward by this number capital sigma omega, if we push forward our C omega A cone by capital sigma omega under the normalized transfer operator, then the diameter in our future cone is going to be finite and bounded by some very specific non-random number delta. Okay. Now, to get the cone contraction argument to work, we only need to push forward by this capital sigma omega one time. And once we do that, we will, from there on, push forward always by either R star or L omega R star, depending on if we're on a good or bad fiber. And so we'll always get this contraction if we push forward sufficiently far. Okay. And so what I was saying is summarized here in this lemma, that if we take, for depending on omega, if we find some, say, n2 of omega, and we take little n bigger than n2 of omega and some L, any positive L, then what we get is that the sequence, by going backwards in steps and then pushing forward in steps, so that we end up on the omega fiber. This sequence, L n of 1 from the sigma minus n fiber, this forms a Cauchy sequence. Well, in terms of the theta plus Hilbert pseudometric on the sigma omega, or on the C omega plus cone, and then using the result from Livrani, Sisal, and Vianti, we can translate that exponential decay in the theta plus Hilbert metric to the soup norm, so that we get that our soup norm of L n of 1 is converging in our Cauchy sequence exponentially quickly. So what all of this tells us is that there must exist some Q omega in the C omega plus cone. Okay, so what that means is there's some function Q in the BV omega space, and some measurable function, we'll say rho, from omega into R, such that we have L omega of Q omega is equal to rho omega Q sigma omega, and that capital lambda omega of Q omega is equal to 1. Okay, so this Q omega is exactly the invariant density that we were looking for. Okay, we defined rho omega earlier to be capital lambda sigma omega of L omega of 1. So like the conformal integral of L omega of 1. But from our cone contraction, we get a second characterization of rho omega as this limit n goes to infinity of this ratio of capital lambdas of L push forwards of 1. Similarly, we get Q omega is this ratio of Ln of 1 over lambda omega of Ln of 1. Now, it follows from our cone contraction that capital lambda is in fact equivalent to a non-atomic Borel probability measure nu omega, and that the support of this nu omega is contained in our survivor set x omega infinity. Okay, so what that means is that our measure nu sigma omega satisfies this equivariance property with our transfer operator for every f in BV. Now, from this invariant density and this conformal measure, we're able to define our invariant measure on the open system. And we let mu omega be Q omega integrated up against nu omega. And from this definition, it's very easy to show that this measure mu is T invariant in the sense that the integral of f of t with respect to nu omega is equal to the integral of f with respect to nu sigma omega. Even more, because we got this exponential contraction, it follows that this measure mu omega satisfies an exponential decay of correlations, which we have down here at the bottom. And here I should point out this multiple, this coefficient d omega is random, and it's well measurable with respect to omega. Now, from all of this, well, we want to look at those two original questions we talked about. And that was, we want to look at the rate at which mass is escaping through the hole. And we want to look at the Hausdorff dimension of our survivor set. Both of those questions we're going to answer by talking about the expected pressure. So let's go ahead and define those. We'll define the expected pressure for the closed and open systems. So we'll say the expected pressure of the closed system, the expected pressure of our potential phi c, well, that's just going to be the integral of log lambda omega c. And we'll define the expected pressure for the open potential phi, which is just our closed potential phi restricted to the complement of the hole. Well, that's just going to be the integral of log rho omega. It's easy to show that the expected pressure for the closed system is greater than or equal to the expected pressure for the open system. And now, our escape rate, we want to define that as just the negative of the limit 1 over n log, well, given any measure rho, it's just going to be the limit 1 over n log rho of the nth level survivor set x omega n. Now, I should say that there's no reason that this limit in general should exist. So really, we should define the upper escape rate and the lower escape rate. And if they're in fact equal, we define this escape rate as I have it right now. But for our systems that we've looked at, this limit does exist. So we've foregone the upper and lower. And in fact, what we can say is that the escape rate for the closed conformal measure, or the escape rate for the closed invariant measure, we didn't previously define the closed invariant measure mu omega c, but we would define it in the exact same way we did with the open invariant measure. That is, we take the closed invariant density and integrate it up against the closed and conformal measure. And what we can show is that both of these escape rates for these two measures is equal to the difference in the closed and open expected pressures. Okay. So from our simple example with the Cantor set and the map Tx mod 3, T of x is 3x mod 1, rather. The closed pressure would just be log 3, and the open pressure would have been log 2. Okay. So that's all of the problem about the escape rate. Now we can talk about the size of our survivor set. Well, we already said that almost every point is going to escape. So that means naturally that our surviving set has to have measure 0. Measure 0 with respect to our closed conformal measure. But we can talk about the finer geometric properties, and we can ask questions like, what is the Hausdorff dimension, or even the Hausdorff measure? So if we want to look at the Hausdorff dimension, we want to consider the family of random potentials that's given by phi c and parameterized by a little t in 0 to 1. Okay, and those are going to be equal to minus t log of t omega prime. If we look at the pressure, the open pressure and the closed pressure for each parameter t, we would form the pressure function. T maps to the expected pressure of phi t. Now, in going back to 1979, Bowen proved for the first time in the setting of quasi-Fuchsian groups that the Hausdorff dimension of the surviving set is equal to the unique 0 of this pressure function. Okay. So in order to get such a result, we're going to have some additional requirements. So additionally, we're going to assume that our weight function g omega c satisfies the bounded distortion property. And what that means is that on each of our partition elements, that g omega n satisfies this bounded distortion property. Okay. And now the last two assumptions is that we'll say that the map T has the large images property if for m almost every omega, this infimum over n over the infimum over all the partition elements of z omega n has positive closed conformal measure if we iterate this interval z n times. And we'll say that T has the large images with respect to X, with respect to our whole H, rather, if we satisfy this property, that for every element of our monotonicity partition that intersects the survivor set, if we push forward in steps, we cover the survivor steps at n steps forward. Okay. Now, if we satisfy these additional properties, then we're able to get our Bowen's formula for the Hausdorff dimension. And what that means is that, well, we're able to show that our expected pressure function is strictly decreasing to minus infinity and convex. And so there must exist some unique 0 in the interval 0 to 1, such that our expected pressure is positive for all t less than this h and negative for all t greater than h. And in addition, if we have these large images properties, then we get that our Hausdorff dimension of our survivor set is equal to this unique 0h for almost every fiber. Okay. And so now, those are the two main questions we wanted to talk about. So I want to go back to our main assumptions. And earlier I said, well, we had these kind of complicated main assumptions, and but we can do a little bit better and make these a little bit simpler. Okay, but in order to really state these simpler assumptions, we need to recall these kind of complicated good and bad partitions that we had. Okay, and these are complicated, well, because this functional capital lambda is really an infinite limit. So ensuring that an interval has positive lambda functional value is not going to be very checkable. Okay. What we can do, like I said earlier, is that, well, if we have a full branch, we can easily check that that has positive lambda functional value without having to take a limit. And so what I want to look at is, instead of these good intervals, I want to look at all of the full branches. So I'm going to construct this z omega in F to be the subset of our good intervals that are full branches, meaning that t omega n of z is going to be equal to the entire unit interval I. And then we'll let the z omega u be the set of all non-full branches. And what we can show is that, well, any bad interval is going to be contained in our set of non-full branches. And any full branch is going to be contained in our set of good intervals. Now, if we restrict to the classes of full and non-full branches, and we accept that our examples need to have some sufficiently large number of full branches, we can come to these alternate assumptions. To state them, I'm going to say, let's let zeta omega n denote the maximum number of contiguous non-full intervals. Okay, so contiguous in the exact same sense that we had from before, but now I'm looking at not bad intervals, but non-full intervals. And if we do that, well, the extra assumptions we need is just that A, we start off with at least some number, some positive number of full branches. So our z omega 1 F needs to be non-empty. Okay, and then we can replace our Q1 and Q2 and Q3 assumptions. Using some work, we can actually boil kind of the three of those down into just this one Q1 prime assumption. And that is that, well, we have what looks like our contracting potential assumption, that is that limit 1 over n log sup g plus some quantity is less than limit 1 over n log rho, integral of log rho. But the integral of log rho is also maybe complicated to check. So we can replace that with a lower bound and in limit 1 over n log inf L omega n of 1. And now the really great part about this assumption that makes it much more checkable is that, well, this additional bit that we have to add on to our 1 over n log sup g is just the integral of log zeta omega, but only on the first level. So I only have to check that I have enough full branches on the first level and not have to calculate how many full branches I have at each in steps. So this becomes something we can check very easily just looking at our map and just the first iterate of our maps. And I guess the Q0 prime and the Q1 prime assumptions work if we add a little bit of regularity to our whole, and we're going to assume that our whole has, well, finitely many connected components, and that the number of connected components on each fiber is going to be log integrable, which is not a very restrictive assumption. Okay. So let's go back then to our random beta transformations again, just to say that, well, all of the alternate assumptions we just gave are very easy to check for this system. Here, the number of full branches we have is exactly equal to the floor of beta omega. And we will always have exactly 0 non-full branches because we've chosen our whole to be exactly the one non-full branch that we have. So it kind of deletes all of the non-full branches. We're left with only full branches and something that's very easy to check. If you want to look at this class of beta transformations and you want to pick a whole to be something else, then, well, it's pretty easy to show that your number of non-full branches is going to be less than or equal to 2, rather 3. So if we go back, oops, that's in the wrong direction. If we go back, there we go. It's pretty easy to show that if you put your whole anywhere else for one of those beta transformations, that your zeta omega 1 number will be at most 3. So you just need to replace this middle term in our contracting potential with the integral of log 5, so just log 5. So this gives us a very large class of examples for which all of this applies. And I also want to say, though, that while beta transformations are pretty simple, they do give some pretty chaotic behavior, but we can also do this in principle for any random system that we talked about in the closed paper with Gary and Cecilia and Sandro. Okay, so that means we can do this for a very large class of Lasota-York maps, general Lasota-York maps, and also maps which are for some omegas can be non-uniformly expanding or even have contracting branches, as long as we see expanding maps sufficiently often. So again, this theory applies for a very large class of maps, very wide class of examples. And with that, I think I'll say I'm done, and thank you for listening, and let me know if you have any questions.